Yes, I know.
It should be on his. There now.
No, 919.2. Hey, good evening, ladies and gentlemen. I'm Chair of the DAO. Firstly, I'd like to acknowledge that we are doing this talk. Start party on the territory of the original territory of the Chocolate people. I just want to add that we're actually talking to members of the Islamic Leadership Council in order to get their participation in future activities. So that seems to be very interesting for all of us. And I urge you to look out for that. This evening, it's my pleasure to introduce
Several decades.
Dr. James Nemec, who is currently at Camosun College. James and I used to share an interest in certain kinds of variable stars, and that's his topic of research. But tonight he's going to talk also a little bit about variable stars, perhaps, which are very key to the early discoveries at the classical intelligence. Oh, yeah. All right.
Yeah.
All right. So, without further ado,
Thanks a lot. Okay, well, welcome to Dominion Astrophysical Observatory.
yeah.
As Ben said, I'm at Camosun College. I've been teaching astronomy courses there for roughly the last 20 years. We have two courses, Astronomy 101, which is about the night sky and the solar system, and the second course about stars and galaxies. And together they basically constitute an introduction to astronomy course that you might find anywhere in North America. But the Dominion Astro, what I'd like to do tonight is basically convince or tell you a few stories about why this observatory here is important. And in the earliest days, there were lots of great things done. And so basically, I'm going to talk about four what I consider big discoveries that were made here at the observatory. Observatory was created in 1918, and at that time, it was supposed to be the world's largest telescope. It got picked by a 100-inch, it's a 72-inch, 1.8 meters. Basically, my height is the diameter of the mirror. Here's an old picture of it. The dome. It was supposed to be the world's largest telescope, but they built a 100-inch telescope overlooking Los Angeles, called the Mount Wilson 100-inch telescope. And then actually, the Los Angeles one was finished roughly 6 months before this one. So it's really the second largest telescope at one time. Well, the story I'm going to say is a little bit personal. This is my father. In just after World War II, in Pisa, Italy. He was from Yugoslavia. When he came to Canada, just like most immigrants, they changed their name. He became Mike Nemec instead of Milenko Nemec. After World War II, he didn't want to go back to communist Yugoslavia. He had enough of communism. And so the deal was he could come to Canada, but he had to work in the coal mines at Fernie for 3 years. He came from a family of engineers. He basically started from scratch. He actually got out of the coal mines. He was a good soccer player. And one day, the Fermi soccer team was playing engineers from Kamloops. My father scored a few goals, and after the game, he got tapped on the shoulder. And the guy said, "How'd you like to come and become an engineer here in Canada? But you got to come play for our soccer team." And that's how he got out of the coal mine and basically became an engineer. The reason I'm telling you that is, well, when he liked astronomy, basically, and he had these astronomy books around. We lived in a trailer until I was 10 years old. And the books, the kind of books we had were written by George Gamow. Birth and Death of the Sun, Biography of the Earth, Creation of the Universe. George Gamow was another guy who didn't want to live in communist Russia. He managed to escape on a canoe one day, just canoed out of the country and eventually got himself a job in the United States. Well, this is a story about this telescope. I first looked through it when I was 5 years old. There I am right there. We had a 1954 Buick. Here my dad got my mom and my brother to haul logs. And we built a raft. This is this Quimel Lagoon. And my mom. And on one of the Saturday nights, we came to this observatory. And I can remember very well the stars that we looked at. It was very dark, and the guy had a fedora hat on and a big trench coat. And we got underneath the telescope. It was a long lineup. Eventually, we got to look through the telescope. And this is what I remember seeing. It's a star called Albireo, also known as Beta Cygni. There's this constellation Cygnus the Swan. And right there is Beta Cygni. And I remember vividly that one star was red and one star was blue, and I was told it's the binary system, two stars going around each other. Well, in George Gamow's book, Birth and Death of the Sun, there's an explanation for why the stars have different colors. So what we got here is our three graphs. Imagine three stars, one a cool star, one a star like the sun, and another star that's hot. Okay. And what we've got here in these graphs, this is the light coming from the star, the amount of light, against wavelength. Okay, now our eyes can only see a limited number of wavelengths, a range here between these dashed lines. This is blue light here. This is the red light. In between, you've got a rainbow of colors. Okay, so notice that in a hot star, a really hot star like this 10,000 degree star, there's more blue light than red light. And that's why the star looks blue, because it's hot. Whereas in this star, well, it's sloping upwards, there's more red light than blue light. And cool stars look red. So what I was seeing was a hot star and a cool star together going around each other in a binary system. A star like the sun has roughly equal amounts of red light and blue light. And so it's not red, it's not blue, it's somewhere in between, yellow. These are called Planck Curves, and they were figured out around over 100 years ago by Max Planck. And this is how you can understand why some stars look blue and some stars look red. Well, here's a page out of George Gamow's book, Birth and Death of the Sun. Here's George himself. He's a very colorful character. And drove a white Cadillac with leather seats and did magic tricks for the girls. Very colorful personality, and you can kind of get a feeling for that. Here he is in his textbook describing another result that's over 100 years old. This is another graph. What we got on the bottom here is temperature, basically. Hot stars on this side, cold stars on this side. And on this axis going up is the luminosity of the star. Now, what luminosity is, you know about light bulbs and the wattage of a light bulb. A 100-watt light bulb is more luminous than a 60-watt light bulb. Okay, so at the top here, we've got the really luminous, high wattage light bulb stars, and these are the fainter ones. And the sun's right in the middle. So the sun's neither really hot nor really cold. And it's also, there are stars that are more luminous and stars that are less luminous. It's called the Hertzsprung-Russell diagram, named after the two people who first figured this out. But this is a really interesting and important diagram, because the question is does the sun always stay at that point? Or does it maybe evolve and get hotter and brighter? Or does it go this way? It gets cooler and less luminous? And how do we get up here? Incidentally, these here are called red giants. Size goes up this way. So these are giant stars, and these are really small stars, white dwarfs. Okay, so some of the other questions are, do stars just stay where they are, or do they evolve? We now know that this is a key diagram for understanding how stars evolve. How do they move? What's going on inside stars? Clearly they're burning, so they must change somehow. And how does that show? Does it show up on the surfaces? And secondly, this is for single stars. Where do binary stars fit in? We've just seen Beta Cygni. It's a binary system. So does that play a role somehow? Okay, well, it turns out that binary systems, that one star just showing you, turn out to be really important. The reason they turn out to be really important is what I've bold-faced here. The more luminous main sequence stars are more massive. Let me back up here. What does that say? It's saying that these stars up here are really massive. And these ones down here are low mass. So if the sun was to go up this way, it would have to become more massive. Well, how could it do that? Well, it could gobble up planets. That's one way. But planets aren't massive enough to make the mass increase by very much. Jupiter is 1/1000th of the mass of our sun, and that's the most massive planet. Okay, so the sun's probably not going to do that. Well, also, what about going this way? Well, it would have to lose mass. The lowest mass star is about 1/10 the mass of the sun. But we don't see any sign of the sun throwing off tons of mass. In fact, we'd have to throw off 90% of its mass, and we just don't see that. Well, we've come a long way since then. We now know what the sun does. What the sun will do is it will go up here and become a giant star. And then it'll go down, it'll go back up. Eventually, it'll wind up down here and become a white dwarf. Right? But this is the key figure, the key idea that allows us to understand evolution. Okay, in any case, let's get back to the observatory here. The first director, the person who was responsible for getting this observatory going was John Stanley Plaskett. And one of his big discoveries was of a binary system. That's probably the most massive binary system out there. It has two 50 solar mass stars going around each other. So just like Albireo, except for being that massive, they also had to be very blue and very hot. And it turns out when you're really massive, you don't live very long. Gravity makes things happen faster. And so this thing probably at some point is going to explode. It'll just go through its life cycle really quickly. In any case, here it is. It's still an important star. It's called Plaskett's star. This was one of the discoveries made in 1922 with this telescope after it was first built. He had a son, Henry Plaskett, who helped him with his observations and eventually became the chief astronomer at Oxford University. Okay, so you all recognize this, the Milky Way. When we look up at the sky, we see the Milky Way, and you probably don't see it this well unless you're at a really dark site. Plaskett was also interested in what the big picture of how our stars distribute. And one of the earliest pictures of what the big picture was William Herschel, an Englishman, actually a German musician who discovered the planet Uranus quite by accident. He thought he found a comet. In any case, he and his sister studied the numbers of stars around the sky, and he thought that, well, this is what the universe looks like. Sun's at the center, and around it are stars, and it's kind of elongated star counts. Well, in addition to counting stars, you just look at the sky and you see that in addition to stars, most of objects look like this, galaxies. And you can see here that it's got these spiral arms, it's got a center. Up until about 100 years ago, we didn't know that if this was what this was. We didn't know what galaxies were. Now we now know, in large part to work done by Plaskett, that our own galaxy looks kind of like this. We live in a spiral galaxy. And what in the early days, what people did was they took photographic plates. They didn't have a digital camera, took photographic plates. And here's an example. And this is actually a nearby galaxy, and this is a star cluster in our galaxy. So another important bit of work that was done here at the observatory was a lady by the name of Helen Sawyer-Hogg. She started using the telescopes here to study these globular star clusters. And she took pictures, not as spectacular as this one, but she took pictures of star clusters. And here's just a quarter of one of those. You can see there are blinking stars. Not all stars have the same brightness all the time. They're not just a constant brightness. You can pick them out here. There are these blue ones here. Anyway, these are they were initially known as cluster variables. And Helen Sawyer-Hogg used this big telescope to study the star cluster, the variable stars in these star clusters. And back to our friend George Gamow. George Gamow, in his book, talks about how you can explain bright variable stars with varying brightnesses. And he does it two ways. He talks about there being a binary system where one star goes in front of the other one and blocks the light. Then it comes out again. And so the brightness changes depending on the total amount of light you're getting. But another way to make a star vary in brightness is to actually have it changing in size and pulsating like this. And we now know that those blinking stars in the globular clusters tend to be of a pulsating variety. And it turns out they're really useful because you can get distances to those clusters if you can find those variable stars. And Harlow Shapley, astronomer at Harvard, big shot astronomer at Harvard, did this for a whole slew of globular clusters. And Helen Sawyer-Hogg, who worked here after she got her PhD, was working with Harlow Shapley. And one of the big results that he came up with was, if you look at where these globular clusters are, once you know their distances, it turns out that if the sun is there, the center of the swarm of globular clusters is somewhere over here. And he correctly concluded that that's the center of our galaxy. We're not at the center. That's the center of our galaxy. And so this was a big deal, using these star clusters and finding variable stars. And that was a big part of the work that was done by Helen Sawyer-Hogg. Here she is in a later picture. But in the early 1930s, this was work being done here. She moved to Toronto, and her husband got a job. They're both major astronomers at the University of Toronto for many decades. Okay, so a picture of our galaxy is we have we're not at the center, we're over here somewhere, and we have these globular clusters going around, and we have a center here. And the Milky Way, what the Milky Way is we're actually seeing the disk from within the disk. It's like as if we were living in Saturn's rings. And we look outwards and we see this band of ring going around the sky. And in one direction, you see this massive Saturn, and the other direction, you see nothing. It's sort of like that. And so the Milky Way is just what we see from our vantage point about 2/3 of the way up in the disk of the galaxy. The reason those variable stars are important, they turn out to be called RR-Lyra stars now, is they all have the same luminosity. It's like they're all 100-watt light bulbs. If you move a 100-watt light bulb further away, it gets dimmer. It looks dimmer. Whereas if you bring it closer to your eye, it looks brighter. And that's why you can use them for getting distances. There are other kinds of variable stars that are even brighter called Cepheids, and sometimes they also turn up in the studies like Helen Sawyer Hawkins do. Okay, so one of my main interests is our Lyra stars, variable stars, and we now have come a long way with the theory of these things. Here's how they change their luminosity. They're roughly 50 times more luminous than our sun, so they're really bright. Over here they are over time, it gets fainter, and then it suddenly rises really quickly in brightness, and then it fades again. And meanwhile, changes its size. And we know a lot about what's going on inside these stars. Okay, the third big discovery I'd like to talk about was made in the 1940s. This guy over here, Andrew McKellar. Was one of the not one of the original astronomers, but he was hired in the 1930s, 1940s. He was interested in what's between the stars, not the actual stars or galaxies, but interstellar. If there's anything between stars. And one of the things you can do with this telescope is you take spectra. That's to say, you pass the light through a prism, and you get a rainbow colors. And by studying that spectrum, you can learn about the source of that light. And he was studying interstellar gas, just the gas between the stars. And one of the things we know about interstellar gas is it's basically cold, because there's usually no stars around, and it's made up of molecules. And well, you all know H2O, right? What H2O is water, right? It's a hydrogen, it's oxygen, it's H2O, so it's an oxygen with two hydrogens. And the way a molecule works is it vibrates. So those two hydrogens vibrate, and it can rotate, and it can move through space. And it usually does all three simultaneously. I can't do it, but you can try it yourself and see. You can do it. But what makes it vibrate is temperature. The higher the temperature, the faster they vibrate. And if you make the temperature really high, the molecule will break up. But in interstellar space, where it's really cold, it vibrates slowly. But one of the surprises he came up with was he found that he expected them to not be vibrating at all where there's no light, nothing to warm them up. And that's not what he found. He found that they were vibrating, but very slowly. And he predicted a temperature. He said 3 degrees above absolute zero, above the absolute coldest temperature you can get. And that was a surprise. He didn't understand it. He wrote in the back of his paper, and at the end, oh, this is the temperature I found, but I don't really understand why it's got that temperature. Okay, well, it turns out, again, back to our friend George Gamow. George Gamow, one of his main science results was what we now call the Big Bang. And here's his student, Ralph Alpher, and they were studying what the universe might have been like in the past. And the big conclusion was, if you go back in time, this is here we are now, if you go back in time, the universe was hotter. This is temperature, this is time. So in the distant past, the universe was hotter. And the idea was that over time, the universe is cooling, just like a coffee cup. Coffee will cool. And the conclusion was that it shouldn't be 0 degrees now, absolute zero, but something a little bit warmer. It's cooling, but it hasn't cooled all the way down to 0. And the prediction from the models is it should be a few degrees above 0. And in the 1960s, it was discovered from radio observations made with this telescope here, that the universe does have a temperature, no matter where you are. There's the lowest limit in nature is around 3 Kelvin. So in fact, Andrew McKellar, who really wasn't interested in cosmology, had observed for the first time the cosmic background radiation, the 3 Kelvin, and seen it in molecules. If he'd lived, he probably would have shared in the Nobel Prize with Penzias and Wilson. Nobel Prize was awarded in 1978. 3 years ago, another Canadian, Jim Peebles, was part of the theoretical group who made the prediction about just how the Big Bang works and the fact that the temperature should be around 3 degrees. I showed you earlier Planck curves. Well, here's the observational data and the model, and the peak here tells you the temperature. Remember, it was over on the right if it's cool, and it was over on the left if it was hot. In this case, it's in millimeters. With such a good comparison of data and theory, the temperature turns out to be 3 Kelvin, which is very close to what Andrew McKellar found with his interstellar molecules. Okay, well, those are my four big science results from the observatory. Kind of used up my 30 minutes. So anyone has any questions maybe about Camosun or about early science? Talk astronomy, talk shop. Anyone here from the States? No Canadian? A few Americans? Two. Where are you from?
Minnesota.
Minnesota, okay.
Are we able to audit those 2 astronomy classes?
No, they're in person.
Okay.
Yeah, so they're basically Tuesday, Wednesday, Thursday are classes, and they're a couple of hour a day on those days.
In the middle of the workday?
Just on the work days, yeah.
Okay.
And they transfer. They're exactly the same as a course at say UBC or UVic. So if you're a student, you can take the credits, and if you ever go to UVic or UBC, you get full credit.
But if you're not a student, just an adult interested in.
You can still take the course.
Yeah, okay.
Yeah. And I have a lot of adults, not a lot, but I have students. Well, we have a solar telescope, which is more convenient because I can set it up, and during the daytime when the students are there, we set it up and we look at the sun, and you can see sunspots, and you can see flares off the side, and it works really well. And students seem to like it. That's more in the stars and galaxies course. We also, for students, one of the things I get them to do is, everyone has a phone now with a camera, is they take pictures of the moon, which they can easily do, it just takes a few minutes, and watch the phases of the moon changing. And then they put together a little file, and they submit that to one of the labs. And people love using their phones for taking pictures now, so popular labs. Yeah.
So the telescope is quite old.
Yeah, 1918.
But it's still being used.
Yes.
So is there a particular niche that it fills now when compared to modern?
Oh, well, they keep up to date with improved instrumentation. My first astronomy job here was at the observatory, actually, as a night assistant. I got a master's degree, and then one day I got a phone call saying, "How'd you like a job at the observatory?" I was told explicitly, it's a dead-end job. Don't expect to make a career out of it. My job was to help the astronomers every night, basically make sure they didn't break the equipment. So I would work 3 weeks on and then 1 week off at night. And it's actually a very interesting job because astronomers from all over North America come here to observe. They usually have maybe a week of observing time or three nights. And so I sit under the telescope with the astronomers and we chat about astronomy in graduate school, and it's a neat job. But the observatory is good. They keep the instrumentation up to date. In fact, the latest thing is they've been doing remote observing. So you can stay at home and control the telescope with your computer from Alberta or wherever you happen to be. Okay, well,
You had a slide with the Milky Way, and it's often described as a disk, it's presented as a disk of light.
yeah, I'll go back here. That's it. Oh, that one. Yeah.
So we just accept that there's a disk there, and there's a halo. It's just to identify relative concentration of stars and galaxies.
It's more to do with the history. The oldest objects are the globular clusters, the ones that we saw pictures of. We think they formed from a big gas cloud and it started to collapse because of gravity. As it collapsed, it formed these globular clusters so that they basically are in these huge orbits like this, around like that. And then what happened is it started to spin faster. Physics is called conserving angular momentum. So it started to spin, so it started to flatten out. So it kind of went from a beach ball to a pumpkin, and then eventually it flattened out into a pancake. So the oldest stars are the halo ones, and the ones that are in the disk are younger. So our sun is about 5 billion years old. But the globular clusters are 10 billion years older than that. So it's really a sequence of evolution of our galaxy by studying these different kinds of stars.
So disk is really more matter than the
Yeah, there's still gas left over from the original collapsing. It's in that disk. And so you need gas to make stars. And so there's still stars forming in the disk out of that gas that's left over.
disk is as much representation of what's there.
Yeah, the disk is rotating. In fact, it takes about 250 million years to make one turn. When did the dinos get wiped out? Who knows when the dinos got wiped out? 65 million years ago. So that's a quarter of a turn. So and the dinos first appeared about 250 million years ago. So let's say we're here. It takes 250 million years to go all the way around. One turn ago, the dinos were on the Earth. They started to appear, then they made 3/4 of a turn, and then something happened 65 million years ago that wiped out the dinosaurs. And then for the last quarter of a turn, well, we've been evolving on the Earth minus the dinosaurs. And so it takes 1/4 billion years to go all the way around once. But we're still forming stars in the disk. And this is I guess the top-down view would be this galaxy picture. There, like that. So we're sitting right at the inner edge of one of these spiral arms. I forgot to mention that another plastic discovery was that he discovered these spiral arms by studying the hottest stars. Even before we actually saw them from radio mapping, Plaskin and Pierce discovered that OB stars follow a pattern that looks like spiral arms. So in fact, spiral arms were also first seen here in Victoria using this telescope. Okay, well, thank you very much for coming. Always got more fun than people. I get to see a picture of my dad. Yeah.
Okay, hi everybody, and we're going to switch over to a different part of the presentation now. I'm just going to make myself the focus for the moment. And we have Jason Beeman helping me here tonight. And Jason, have you noticed any questions on YouTube so far?
No, none yet. I think there's only a couple of viewers on YouTube.
Okay.
But it was nice to actually hear all the people asking them in there. It's nice.
Yes, you could actually hear that. So everybody, this is kind of an experiment with trying to get the audio working correctly and so on. So what we're going to do now, though, is we're just going to do what's up in the sky, and then we'll do a brief Ask an Astronomer session here. And so the first thing I'm going to do is I'm just going to share my screen, and I'm going to, hopefully you can see this. You should be able to see a sunspot. Can you see that, Jason? A big sunspot here?
Yeah, no, that's a really good size too, eh?
Yes, so this is actually what's visible right now, and this image at the top left is probably a better representation of it. So this is actually a series of sunspots making a big group, and it's so big that if you're to put this group, one end of this group near the Earth, the other end would be about a third of the way to the moon. So it's absolutely huge. And there's a temptation to try to observe these so-called naked eye sunspots directly, but really shouldn't call them that, because I think it encourages people to actually use their naked eyes to look at the sun, say around sunset or through the fog or something. And we never want to do that, because you can actually damage your retina without even feeling any pain. So we don't want to do that. So one of the ways of doing it is to get an expensive solar filter or proper eclipse glasses from a reputable source. But if you don't have that, there's something else you can do. And I'm just going to share, hopefully flip to a different view here. And I have, unfortunately, this little thing at the top here that makes this a little bit tricky. So just bear with me while I try to do this. Live TV, folks. Isn't it fun? Okay, so here's what it looks like. And on this end, you have what appears to be an eclipse, and you don't actually need an eclipse to use a device like this. Obviously, if you just want to see a nice big sunspot on the sun, you can build exactly the same device. And so what we have here is a piece of paper or cardboard with a pinhole in it. What I actually like to do is I like to cut out a piece of cardboard and then cut a fairly good sized chunk in that, maybe about 5 centimeters across, and then tape some tin foil over top of that, and then poke a hole in that with a tack. And you have to do this very carefully so that the hole isn't too big and the edges aren't too raggedy and so on. And then some distance away, it could be half a meter, could be a meter, more the better. You want to have a piece of white paper, and preferably on another piece of cardboard. Just tape it to it, and you should be able to project the sun onto that. And if you get really fancy, you can put this all in a big box so it's nice and shielded and dark inside, and then just kind of peek into the box and look at the image. And there's some people, what they do is they try to make the image, make the hole bigger, thinking that they're going to make the image bigger, but that actually wrecks the pinhole effect and you lose the quality of the image. So if you want to make it bigger, you have to actually move the paper further back. So there's a bit of a trick to that. And this is actually on the time and date website that you see right here. So I put that link on the Facebook page if you want to go and find instructions on making this. And what we're going to do now is we're just going to flip over and have a look at the morning sky. Can you see Stellarium, everybody? Hopefully you can see Stellarium. Jason, can you see it?
No, not yet. Just give it a second.
Oh, okay.
Here.
All right. I can try to reshare here. Let me try that again. It's pilot error. I think I was doing it wrong. Okay, hopefully you should be able to see that.
There it is.
Okay, definitely pilot error. And if you've ever seen me do this, you know I have to make at least one big mistake every night. So I think hopefully that's my mistake. So in any case, this is in the morning, and this is at approximately, let's have a look at the time. This is about 3:41 in the morning, and I don't know about you, but I'm not usually up at this time, but it's still sufficiently dark that you can see both the planets and a dark sky. And what we're looking at here is the waning gibbous moon. So the moon rises at about 2:12 a.m. Tomorrow morning. And but you can see the planet Saturn above it. So if you wanted to find planet Saturn, this would be a good time to look for it. And you can see also that that Jupiter and Mars are over there. So let's just double check the time here. This is actually a little bit after moonrise, so this is 3:42, as I said. And if we just advance the time a little bit, and I'll just go until starting to get light here now. And you can see Jupiter and Mars are coming up. There you can see Venus over there rising up at about 20 after 4 in the morning. And as we move along here, what should see in about, I think if we advance here to early next month, let me just advance to the 5th and just move this over a little bit. See if we can do this properly. You might also see Mercury coming up, but it's going to be really hard to find because it's going to be in the twilight, and Mercury is notoriously hard to find anyway, so you'd actually need binoculars to see it. But if you go a little bit earlier than that in the morning, what you'll see is a spectacular sight with virtually all of the naked eye planets in a line. So, and there's Saturn over there. So that's something to look forward to early next month. And if you're having trouble finding the planets, look for the moon near Jupiter and Mars on the morning of the 25th, and near Venus on the 26th. And so that's something to look forward to. And just to take a quick look at the evening sky now, I'm just going to move it back a little bit and just leave it on that date, but we'll just move the time. And at this time of the year, you can actually see that Capella is going down towards the horizon like that, and but the summer triangle is actually coming up now, and Altair is the last to rise. So tonight, I believe at about 11 o'clock at night, the Altair is actually still below the horizon. Let's see if I can advance this to the right date. So Altair is still below the horizon at about 10:30 to say 11 o'clock at night. But very soon in the early evening, we'll actually have the entire summer triangle above the horizon. There will also be a meteor shower, possibly on May 30th at 10 p.m. Pacific Daylight Time. But apparently it's going to be an all or nothing event. It's either going to be fairly spectacular or we won't see anything. And this is due to a prediction about debris from comet 73P, see if I can pronounce this right, Swasman-Bachmann 3. So I'm going to be looking to see if I see any meteors that night. Jason, do you have anything to add right now?
Well, I was actually just looking. I have a fun little app on my phone, and it likes to tell me all of the nice little events, astronomy events that are happening. And for those of you that are able to see the moon tonight, I believe Saturn is actually really close to it, enabling for some nice little fun look through telescopes if you can get it. So
that's right. Yeah. So maybe we can just move over here to the southeast horizon and then just advance the time a little bit. And there's the moon coming up with Saturn above it. Hopefully you can see that. So that'll be in the southeast. And this is at approximately, unfortunately, 2:50 in the morning. So you might want to have a little nap and set your alarm and so on and get up.
You don't get to sleep if you're an astronomer, so it's all right, I guess.
So, okay. So I guess we can move on to Ask an Astronomer now. And does anybody have any questions they'd like to ask, perhaps in the chat? And you're not obligated to, but this is kind of an experiment, so it might be kind of fun if you did ask a question. We'll see if we can see how this works online. So And anything coming through? Okay. Uh,
Oh, yeah, there's a nice question about the alpha, beta, gamma work.
mhm.
Um, and it's about the beginning of the universe and like that whole nuclear process. And it was done by alpha and beta, and they just couldn't pass it up. So they actually got Gamma to like write a little blurb about it so they could get the alpha, beta, gamma paper out. And it's still like one of the best, nerdiest things that's ever happened. It gets
Well,
really entertaining when you get that. Yeah, the first three letters of the Greek alphabet. But the paper is about that beginning sensation, like you guys have seen that plot where the temperature went up as time went, as time you backed up time. And it was a big issue, like, you know, hey, how do we get everything that we use nowadays? Like, how did stars come to be? We kind of understand that stars make heavy stuff, but what made stars? And so this alpha, beta, gamma paper goes into that in detail, and like the kind of nuclear reaction chains, the timing required, and it's actually still used today. When if you ever see the really fancy simulation with like, oh, the dark matter universe, all that fun stuff that Professor Julio Navarro does at UVic, you'll see like that actually still runs on the alpha, beta, gamma of paper. So yeah, it's great. But yeah, bringing up that gamma there, all he did was just write like a couple lines so they could get his name on the paper.
I'm so glad you're here because I totally forgotten about all of that. I learned that years ago. So thank you for sharing. So we have a question I might be able to handle here. It's from iPhone here. It says, not that fun of a question, but what time do the sidewalk telescopes and Plaskett stay out viewing at the center tonight? And they close her up around 10:30 because we have to be able to get people off the hill. So yeah, so it shuts down a little bit before closing time.
Yeah, you guys got to be on the other side of the gate by 11, or I believe, or something
Yeah,
like that.
I think
Yeah.
so.
So by all means, go on the other side of the gate and set up a telescope, and you can be up there till 2 or 3 in the morning to watch Saturn.
Mhm. That's right. So if you're a volunteer, especially through the RASC, you can you get some special privileges that way, and it's a great little community. So a few little perks like that.
Yeah, no, it's actually really nice, especially being a part of that group and being able to go up onto the hill, and you just get the stunning views and the ability to hang around this atmosphere of astronomy that well is the lifeblood of that hill, and for almost everybody here, I'd say. So
Yeah. And one of the things about that site, aside from it being just a little bit darker than some of the suburbs of Victoria, like where I live near Hillside, it's noticeably darker still. It's above a lot of the ground fog, and I really notice a difference when we come down the hill. It just adds a little bit of a haze to the sky, and so I was asked this week about that, like why did they pick this site? And even though the hill isn't really that high, it just gets it above a little bit of fog. That wasn't actually the main reason, of course, that they picked the site, but this is why astronomers, in part, like to put their telescopes on bumps. So it's it's usually in modern days, it's to get it above most of the atmosphere to improve the image quality. But in this case, it had just that very little practical side angle of getting above ground fog as well. And Jason, I don't know if you want to add anything to that. I could actually explain just a little bit more about that too. It's so
yeah,
they did look at sites across Canada for this, and the site was really picked for the most part for the image quality, and that was really due in part to the minimal day to night temperature variation because we're surrounded by water here. And so the image tends to be fairly stable at night. You don't get the ground releasing a lot of heat right after sunset, causing a lot of air turbulence and blurring the images. But it has a little side effect too, in that if there isn't a big temperature variation, then the metal in the telescope doesn't change very much. And the original plate glass mirror didn't change that much either. And that was a concern because they didn't want to have to waste the first couple of hours of the night as the telescope stabilized and the temperature settled down. So there's a couple of factors there.
Yeah, and also like back where I'm from, the temperature ranges in like throughout the year is almost like 100 degrees. It goes from like plus 30 to minus 30, whereas here in Victoria it's only, you know, plus 30 to maybe minus 10 in the winter. So that stable temperature is super key in engineering to not have stuff shift regularly in other things. But with telescopes, when you know, everybody's used binoculars and all of a sudden like, oh my goodness, everything's moving, that gets really important the bigger your binoculars or telescope is. So having this stable temperature is just essential for that kind of engineering and technology that's required to do the science that Plaskett's been able to do for over 100 years. So
yeah. Okay, are there any other questions? Anything on YouTube? It's a pretty quiet night. I guess everybody's on the hill tonight. That's
yeah, no, it's actually really great. I saw a couple people filtering in and I was like, yay, they're back. I might have to set up my table again.
Yeah, so this is all an experiment, everybody, and hopefully you're enjoying being able to dial in like this. And we're going to keep these hybrid sessions going. We did receive some money from Victoria Foundation, which was in part to do this kind of thing, in addition to paying for the school tours and so on. So so hopefully we'll always have this, as to be able to reach people outside of Victoria or people who can't get up the hill for some reason. So I think we'll end it here at this point. So thank you for attending, and hope to see you again.
No problem. Thanks very much for having me. And yeah, as always, guys, come up to the hill as often as you can. It's honestly, it's a great experience and super great history and a really great group of people. So.
Okay, thanks everybody.